balance as a consequences of this global warming. Therefore, we must find a suitable alternative renewable energy or energy solution to resolve the issues associated with the use of non-renewable energy sources such as possibles. So, among the different renewable energy sources, solar energy is one of the most abundant energy source available on the Earth. It is well known that enough sunlight reaches us every 15 minutes to power the whole world for an entire year. Additionally, it is a safe and clean energy source that powers homes, businesses, and the power plants everywhere. So, how we can utilize this solar energy? So, solar energy can be utilized directly or indirectly in a variety of aspects, such as solar thermal, photovoltaics, that is solar cell, and artificial photosynthesis, as well as solar heating systems as well. Among these, the photovoltaics, that is a PV technology, employs a solar cell or a solar PV arrays that we call it as solar panels to convert the energy from sun into the electricity, which can be used to power the equipment or to recharge the batteries. Whereas this artificial photosynthesis is a way of mimicking the natural process that plants use to create the energy from sunlight, CO2, and the water. It is a chemical process that converts the water and the carbon dioxide into oxygen and hydrogen and the carbohydrates respectively. So this term artificial photosynthesis is commonly used to refer any scheme for capturing and storing the energy from sunlight in the chemical bonds of the fuels, that is a solar fuel. So people also call it as a solar fuel. So solar or the photoelectrochemical water splitting converts this water into the hydrogen and oxygen, and which is a major research topic of the artificial photosynthesis these days. In these regards, we are focusing on the utilizing the sunlight to produce the electricity and as well as this clean H2 fuel using this earth abundant copper chalcogenide compounds, not only limited to copper chalcogenide compounds, but we are also trying to explore these phosphide based, nitride based compounds as well. But today mainly I will be talking about this copper chalcogenide nanocrystals. So basically these copper chalcogenide nano compounds are earth abundant semiconductor compounds that we are fabricating in our lab, which I will present in my next slides. So let's start with the thin film solar cell based on the Kestrite CZT-SSC thin film solar cell absorber. So in this work, we introduce a facile process to partially substitute the copper with silver in this CZT-SSC lattices that enable a device efficiency over 12%, which is very close to the world record efficiency of 12.6% for CZT-SSC thin film solar cell devices reported by IBM. So before we actually get into the experimental results, let me get some background knowledge on why CZT-SSC thin film solar cell. So this graph shows the evolution of the solar cell efficiencies of different thin film solar cell technologies. So recent sensation of this Haller perovskite solar cell technology has achieved a world record efficiency of about 20.55%. I guess recently it has been improved to 25.6% within a span of less than 10 years. Whereas the chalcopyrite CIGS thin film solar cell technology, that's a green one, has achieved an efficiency of 23.4% over several decades, starting from about 1980s, and has already been commercialized. Of course, you can't see the data below 2000. Yes, yeah. The efficiency of 23.4% for CIGS, that's chalcopyrite thin film solar cell technologies, whereas the 25.5% efficiency of this Haller perovskite is definitely a groundbreaking research. And however, the problem with this Haller perovskite is their stability as well as the toxicity issues associated with the lead element the present in this Haller perovskite thin film solar cell technologies. Whereas the problem with this CIGS thin film solar cell technology is that it contains the elements which are not earth abundant, and their scarcity is limited in the earth crust. So as an analogous to this chalcopyrite compound, that is CIGSSC, the Kestrite CZT-SSC compound has achieved a world record efficiency of around 12.6% in 2014, and the paper came online in 2015. So which is less than that. So the record efficiency has been achieved in less than 6 years, starting from 2008 by Professor Katagiri from Japan. However, this efficiency of 12.6% has been stagnant to 12.6% since 2014. Sorry. Yeah. So why we are interested in developing this Arthamadhan CZT SSC thin film solar cell? As I mentioned, though the perovskite solar cell has achieved the efficiency is over 25% in such a short time, they contain a toxic lead and their stability is very poor, which might significantly impact their large-scale utilization uh, for a wider use. On the other hand, the CIGS thin film solar cell technology record with a record efficiency of 12.3%, which has been already commercialized, contains the toxic and the rare indium and the gallium elements, which again raises a question of the elements of this element in the near future. In these regards, the CZT-SSC compound are imaged as a promising next generation absorber compounds, which can be derived from the CIGS by usually like let's say CIGS or the CIS by partially replacing the zinc by partially replacing zinc and tin with antimony. Similarly, this copper antimony sulfide, that is CuSbS2, of course, this compound has four different phases, but we are mainly focusing on the copper antimony, that is CuSbS2, because of its optimal band gap energy for high efficiency conversion of the sunlight into the electricity or the H2 fuel. So we'll be mainly focusing on the CuSbS2, which has achieved the efficiency of 3.22%. Again, because both of these compounds have a high absorption coefficient over 10 to 4 per centimeter square per centimeter, and suitable optical band gap energy of about 1.0 to 1.5 electron hole for CZT-SSC. So we can achieve this wider band gap, so variable band gap energy in between 1 to 1.5 electron hole by varying the selenium content, or as well as by partial cation substitution of the either zinc with a germanium or copper with a silver, and many more. Whereas the copper antimony sulfides band gap energy can be tuned from 0.9 to 1.7 electron hole by tuning the composition of this copper antimony sulfide. Both of these compounds are the environmental friendly. That is, both of these compounds contain non-toxic elements and also low cost and earth abundant elements. So this graph shows the progress in the device efficiencies in CZT-SSC thin film solar cell. So with the first device efficiency of about 2% by category in 2001 using the evaporation method, a lot of groups came up with the different deposition technologies such as the evaporation, PLD, sputtering, nanocrystal based sol gel, and electrodeposition, and showed a record device efficiency of 12.6%, which is about here by this IBM, Wong et al., IBM USA, using this hydrogen-based solution approach. However, however, of course, as an analogous to chalcopyrite, the researcher followed the similar trend to that of the chalcopyrite CIGS compound that led to achieve the record efficiency of 12.6%, just 15 years. However, it has been stagnant since 2015 or 2014. Let's say 2014, because the efficiency was reported in 2014, but the paper was published in 2015. However, a key issue of the stagnant PEC of 12.6% since 2015 is large open circuit voltage depth characteristic, which I will discuss in my later slides. So how we can fabricate this CZTS or ESSC, CZTS or copper antimony compounds using different deposition techniques. So this slide shows the schematic presentation of the fabrication process of the CZT-SSC as well as the copper antimony sulfide compounds. Of course, these both compounds share a kind of similar properties. So probably the fabrication technologies or the fabrication methods used are quite similar to each other, such as this sputtering, evaporation, PLD, electrodeposition, chemical deposition, sol gel, ink-based, or the chemical. So my group is mainly working with these sputtering-based methods as well as these ink-based methods. So ink-based methods are usually, we make these quantum dots or the nanocrystals of these copper, zinc, tin sulfide nanocrystals, as well as the copper antimony sulfide nanocrystals. And then we then process this ink-based nanocrystal into the thin films, simply using the Dr. blade or the spin coating or screen printing. into the thin films, and then we sulfurize or the selenize into the sulfur plus selenium mixed vapor atmosphere in the range between in the temperature range between 500 to 580 for a time of about 5 minutes to 10 minutes, depending on the sulfurization unit that we are using. Yeah, so let's go ahead. Sorry, yeah. So this slide shows the schematic, not exactly the schematic, but the photographs of the sputtering method, as well as the rapid thermal processing unit that we use to sulfurize the CZT-SSA as well as the copper antimony sulfide thin nanocrystal based thin films. So the actual photograph of the sputtering system, then rapid thermal annealing process, the schematic of how this rapid thermal annealing process has been carried out using the sulfur and the selenium mixed powders in a graphite box, and the photograph of the precursor film deposited using the sputtering, and the actual photographs of CZT-SSC thin films after the selenization using this RTB. So this is how like we usually deposit the CZT-SSC thin films using the sputtering methods followed by the annealing. Once we deposit and the sulfurize this CZT-SSC thin films in the RTA, we then proceed further to deposit the different ore layers on the top of the P-type absorber, that is CZT-SSC or the copper antimony sulfide. So usually these ore layers are deposited. So to form the PN junction, we usually deposit the cadmium sulfide using the chemical bar deposition methods. So these are the photographs of the chemical bar deposition methods that we use in our lab. After the deposition of this N-type series buffer layer, we usually deposit the N-type window layer, which is of like 15 nanometer intrinsic zinc oxide and the 500 nanometer of the aluminum doped zinc oxide, and followed by the top contacts such as the aluminum or nickel using the evaporation or either sputtering. And then, yeah, so okay, so this is actually how the solar cell we usually fabricate in our laboratory here at UNSW, as well as back in my previous group, the Chulalongkorn National University, South Korea. So as I mentioned earlier in my previous slides, the device efficiency of this CZT-SSC thin film solar cell has been stagnant to 12.6% since 2015. A major reason behind this stagnant efficiency is a large VOC defect characteristic that caused the efficiency has been that was actually the stagnant efficiency in this SSA thin film solar cell. So it has been demonstrated that the high anti-side defects associated with the CZT-SSC thin films, as well as the associated band tailing caused by the cationic disorder, as well as the unpacificated defects at the interface between the CZT-SSC surface and the N-type buffer layer are the major causes for this large VOC defect characteristic in the CZT-SSC thin film solar cell. So several approaches have been reported to improve this VOC defect and the band tailing characteristic, such as first is like precisely controlling the compositional ratios of this copper over zinc or the copper over zinc plus tin and the zinc plus tin, copper over zinc or zinc plus tin, as well as the annealing conditions like temperature, time, and the initial stage pressure, as well as the different additives such as the tin, because tin is usually easily evaporated during this annealing process. So the people have demonstrated that employing the additional tin or the tin sulfur powder might help to reduce these defect densities associated with this tin-based vacancies. The second approach is controlling the band element between the absorber and buffer layer, that is CZTS and the CDS. So actually we can control this band element by using the alternate buffer layers such as cadmium zinc doped cadmium sulfide. We usually call it as a cadmium zinc sulfide, or the zinc oxide sulfide, indium sulfide, or the zinc tin oxide, or the copper aluminum oxide, or by partially alloying or replacing germanium or silver or cadmium somewhere. Sorry. Yeah. Okay. Third one is the passivation in the junction region using the wider bandgap materials. Again, same like zinc oxysulfides or this cadmium zinc sulfide or zinc tin oxide or the copper aluminum oxide. And fourth one is introduction of the alkali metals such as the sodium, potassium, or lithium occupying this copper vacancies defect sites. Among these approaches, the partial substitution of the copper by the zinc side. So probably here you can see why we are using the silver alloying in the CZT-SSC thin film solar cell to overcome this large VOC defect characteristic of this CZT-SSC thin films. So probably the partial substitution of the copper side in the silver in the crystallized system attracts the most attention and is usually is considered as a promising because the radius of the silver is 1.14 Armstrong, which is substantially larger than that of the radius of the copper, which is only 0.74 Armstrong. So based on these density functional theory calculations, here you can see this plot. You can see this graph. The partial substitution of the copper side by Ag in the crystallized system. Based on this density functional theory calculations of the ACZTSSC, we can tell that the consequently this intrinsic defect densities like Ag over zinc, and the zinc over Ag, and the andesite defect related clusters like Ag over zinc plus zinc over Ag, or twice Ag over tin, or plus tin over zinc are expected to be an order or more magnitude lower than the that of CZT-SSC system. Additionally, the transition energy levels of the Ag and the zinc related defects are usually shallower, indicating that the band tailing caused by this cationic disordering is much smaller in Ag substituted CZT-SSC than the CZT-SSC. So considering these all benefits, we decided to simply alloy the silver into the CZT-SSC absorber to overcome this large VOC defect. So what we came up with with an idea of simply depositing the Ag layer on the top of this copper, zinc tin copper metal precursors using the evaporations of the thickness around 18, 16, and 24 nanometers, and then followed by again sulfurization sulfoselenization in using the rapid thermal processing in the temperature range between 500 to 580 for about 3 to 5 minutes to get this silver alloyed copper zinc tin sulfide thin films. So we fabricated the thin film solar cell devices using the device fabrication line that I showed in my earlier slide. And these are the cell parameters of this silver substituted CZT-SSC thin film solar cell and also bare CZT-SSC thin film solar cell. So you can see that the VUCJ, CPL factor, and the PEC parameters of this silver substituted CZT-SSC thin film solar cells increase initially with the thickness of the Ag layer from 0 nanometer to 8 nanometer. Then it decreases with a further increase in the Ag thickness, which is about 16 and 24 nanometer, except for the JSC. Because there is a trade-off relation between the thickness of the Ag layer with the current density. The trend of the efficiency in the sample A, is which is a relatively high copper content, shows a steady decrease with increase in the Ag thickness. You can clearly see from this graph. Thus, what we achieved is we achieved the optimized highest efficiency of about 8.13% with the open circuit voltage of about 509 millivolt and the JC of about 31.76 milliampere per centimeter square and the fill factor of 50 and the VOC of 602 millivolt. By simply varying the Ag layer thickness, or in other words, we can say by simply tuning the composition of the Ag into the CZT-SSC absorber layer. So what we did is once we optimize this 8.13% efficiency by partially substituting the silver at the copper sites, we optimize the different parameters of this CZT-SSC, bare CZT-SSC thin film solar cell, and then we achieved the efficiency of about 12.07%, which is the record efficiency we have achieved in our group. So what kind of the optimization we have carried out is that we initially controlled the compositional ratio, as well as we introduced the soft annealing process after the precursor deposition and before the final cell post-elimination of these precursor layers. Also, we optimize the band gap in CZT-SSC by finely tuning yes to SE content in the CZT-SSC. Also, we optimize the thickness of this CDS buffer layer. And finally, we also optimize the annealing pressure. So this all work has been done and have been reported in different papers, which I have not included in this presentation because of the time limitations. So as you can see from the table, there is a clear improvement in the device efficiency from about 10.67% for a CZT-SSC to about 12.07% for silver alloyed CZT-SSC thin film solar cell. So it can be seen that this age substitution drastically improved the VOC from 489 millivolt to 572 millivolt, as well as the fill factor from about around 60 to around 63.35%. This improved fill factor, we believe that is the result of the reduced the series resistance, of course not shown here, whereas the improved VOC suggests the reduced recombinations in the spectral region. Of course, I will discuss this in my next slides, where we carried out these advanced electrical characterizations to confirm our hypothesis. Also, we find out that the minority Carrel uptime of this silver alloyed CZT-SSC thin films was improved to 3.94 seconds compared to this CZT-SSC, which showed about 3.43 nanoseconds, which again confirm the reduced recombination rate at the junction interface between the absorber and the bubble. We also further carried out the Arbach tail energy to prove these observations. So Arbach tail energy values were calculated to be 31.92 milli electron volt and 28.18 milli electron volt in CZT-SSC and the AG alloyed CZT-SSC thin films solar cell respectively. Moreover, for both devices, the portion of the PL peaks are shifted towards the lower energies, rate shifting with respect to band gap determined by EQV. So you can see here, the band gap from the EQV was obtained to be around 1.078 electron volt, whereas this is for CZT-SSC and this is for silver alloyed CZT-SSC. So this band gap energy, the energy gap between the age from the band gap measured from EQV and the PL are about 52 milli electron volt in case of the CZT-SSC and about 33 milli electron volt for silver alloyed CZT-SSC, indicating that the reduced band tail characteristic by introducing the silver in a castorated system. So we carried out these microstructural characterizations as well as this electrical characterization, that is CV, of this CZT-SSC as well as the silver alloyed CZT-SSC thin film solar cell devices. So the cross-sectional TM images of this CZT-SSC and the silver alloyed CZT-SSC shows that there is no significant differences in the microstructures even after the age substitution. However, this electrical characterization suggests there is a significant improvement in the electrical properties after the silver alloying in the CZT-SSC lattices. So the pre-charge density value is found to be the smaller, which is about 2.07 into 10 raised to 15 centimeter raised to -3 in case of the silver alloyed CZT-SSC, whereas it was found to be about 4.99 into 10 raised to 15 centimeter raised to -3 in case of the CZT-SSC. Whereas, okay, these values further explain our observation of the improved band tailing characteristics as well as the VOC repeat characteristic as a result of the reduced formation of the copper over zinc antisite defects or the copper vacancies point defects. So, okay, I'm not going to go into much detail of this one. Finally, let me conclude a work about this one. So what we believe is that so benefiting from the silver alloyed CZT SSC or AG substitution, partial AG substitution in the CZT SSC devices, and the further optimization of these device parameters such as annealing pressure, sulfuration time, or the thickness optimization of this N-type CDS buffer layer, and many or more other parameters. The efficiencies over 12% can be easily achieved with the low VOC debit characteristic of about 528 millivolt in case of the CZT SSC thin film solar cell. So this is all about the CZT SSC thin film solar cell. Now I will briefly explain about our work on utilizing the copper antimony sulfide, which is another copper chalcogenide based compound for their application in solar H2 fuel. So most of you must know that so to synthesize these colloidal nanocrystals of the copper chalcogenide compounds, the people they usually employ this long carbon chain organic solvents such as the oleamine, octadecene, oleic acid, which are kindly toxic organic solvents, as well as they are very difficult to get rid of during the purifications because they contain a long carbon change. Also, once you make these nanocrystals using these long carbon chain ligands, such as the oleamine or the oleic acid, during the sulfuration of the cell nitrogen, they usually gives you the carbon residues, which eventually impacts your final device performances of this nanocrystal-based thin film solar cell devices, as well as this nanocrystal-based photoanodes or photocathodes for solar H2 production. So considering this in mind, what we did is we demonstrated the use of deep eutectic solvent, that is ethylene, as a low boiling point solvent, as well as the low viscosity and non-toxic solvent for the synthesis of this copper antimony sulfide nanocrystals and its all 4 phases. So this deep eutectic solvent is a new generation of inorganic new generation of the ionic salts based on the ionic liquids, which are generally prepared by mixing simply a Lewis acid with the Lewis base at a certain molar ratio. Of course, I'm not going to go into much details, as you can find the detailed information in our recently published article in JMC. So we synthesize 4 different phases of these copper antimony sulfide nanocrystals, such as Cu3Sbs4, Cu-Sbs2, Cu3Sbs3, and Cu12Sb4S13, with the nanocrystal sizes of about 7 nanometer, 11 nanometer, 25 nanometer, and 60 nanometers. The synthesis of these latter 2 phases, that is Cu3Sbs3 and the Cu12S4S13, were found to be very critical, and they always showed the secondary phases associated with this binary antimony sulfide and ternary copper 12Sb4S13, as well as Cu3Sbs4. And in case of Cu12Sb4S13, it's a binary phase of the copper sulfide and the copper 3Sbs4. We believe that because of this critical composition ratio of this copper over antimony and over a sulfur, it is quite difficult to form the phase pure phase of these 2 compounds using the method or using the solvent that we propose in this study. So in our next studies, what we did is we just focused on this only 2 phases of this copper antimony sulfide nanocrystal, which is copper 3Sbs4 and the Cu-Sbs2. And we carried out the different characterizations, and we studied their application in solar hydrogen production. So before I go into the actual application, I will we also carried out the density functional theory calculations to calculate the band structures as well as the theoretical band gap energies of these compounds, which exactly matches with what we observed using this experimental observations. So we further process actually. So once we synthesize these nanocrystals and then the characterizations to find out the band gap energy and the phase purity of these nanocrystals, we actually just focus on this copper antimony sulfide, Cu3Sbs4, and the copper antimony sulfide and nanocrystals, and then we process these 2 compounds into thin films using nanocrystal ink by spin coating methods, followed by the annealing at around 300 to 400 degrees centigrade in a sulfur atmosphere to form these thin films of these compounds. And then we further studied the application into the solar hydrogen production by using this compound as a photocathode and the platinum as a photoanode uh, uh, and AgAg cell as a reference electrode. So as you can see from this photocurrent density versus the potential graphs, actually it is a solar to hydrogen production graph, we can say simply. So you can see the bare Cu3sbs4 and the CuSbs2. Bare Cu3sbs4 and the bare CuSbs2 usually showed very low photocurrent density because of course, like these are just p-type compounds and there is a no n-type junction with these compounds. It means there is a less probability of the charge carrier extraction from this p-type compound, which eventually led to a low photocurrent density in both of these photocathodes. So in order to improve the photocathodes as well as the stability, what we did is we put the platinum as a catalyst on the top of this Cu3sbs4 as well as the copper antimony sulfide platinum, and we observed a slight increase in the photocurrent density in both photocathodes. However, the increment in the photocurrent density was not drastic. What we did is next is that we employed the n-type layer, that is a series in between this copper antimony sulfide and the platinum, also to form the p-n junction between the p-type Cu3sbs4 and CuSbs2 and the n-type series. So after introducing this n-type series into these both photocathodes, we observed a significant improvement in the photocurrent density, where we achieved about 1.28 milliampere per centimeter square current density in case of the Cu3sbs4 photocathode at zero potential versus RHE, whereas 2.72 milliampere per centimeter square in case of the copper CuSbs2 composition. Of course, a difference in the current density in these two photocathodes is where the CuSbs2 showed slightly higher photocurrent density compared to Cu3sbs4 because it is optimal bandgap energy of about 1.62 electron volt, which might absorb the most of the visible light energy. So we also studied the stability of these both photocathodes, and we found out that there is a slight decrement in the photocurrent density after 2 hours of the stability test measurement in both compounds. Again, this poor stability in both these compounds can be attributed to the either loss of the platinum or absence of the suitable highly stable catalyst on the top of this copper antimony sulfide, that is Cu3sbs4 CDS and CuSbs2 CDS. So what we did is next, using the same copper antimony sulfide and like Cu3sbs4 compound as well as the CuSbs2 compound, we carried out the ultraviolet photoelectron spectroscopy characterizations, and we found out the band element of these two compounds, and we established the band element of these two compounds with the TiO2 photoanode as well as the NiO, that is nickel oxide, as a photocathode, and we sensitize this copper antimony sulfide quantum dots either on TiO2 or on nickel oxide to form the photoanode and the photocathode in the same bath. So what we did is we sensitized this Cu3sbs4 quantum dots on the nickel oxide, whereas we sensitize this CuSbs2 quantum dots on the TiO2, again depending on the band element of these two compounds with the TiO2 and NiO respectively, that we calculated using this ultraviolet UPS spectroscopy. So these are the TM images. Of course, I'm not going to go into details. You can clearly see that there is a complete there is a sensitization of this Cu3sbs4 nanocrystals or quantum dots on the NiO nanoshades, whereas you can clearly see the sensitization of this copper antimony sulfide CuSbS2 nanocrystals or the quantum dots on the top of this TiO2 nanorods of this, which we further confirm using the high resolution TM, that is HRTM. And we confirm that, of course, there is a sensitization of this Cu3SbS4 nanocrystals on the NiO and CuSbS2 nanocrystals on the TiO2 nanorods. So after we confirm the sensitization of these two nanocrystals on two different like TiO2 nanorods and the NiO nanosheets, we measured their performances again initially using the 3 electrode configuration by employing 1 molar KOH electrolyte. So we measured initially the performance of the bare NiO and then Cu3SbS4 sensitized NiO, and then this zinc sulfide passivated Cu3SbS4 NiO, and similarly in case of the potanode, that is TiO2 CuSbS through S2 sensitized TiO2 and the zinc passivated this potanode. So what we achieved, the NiO showed a very less photocurrent density of about 0.23 milliampere per centimeter square, which was again improved to about 0.59 milliampere per centimeter square after sensitization of this Cu3SbS4 phase or the composition quantum dots or nanocrystals, which was again improved to about 0.89 milliampere per centimeter square after zinc sulfide passivation. In case of the potanode, we again achieve similar. We again observe the similar trend. So there is a increment in the photocurrent density from about 0.58 milliampere per centimeter square for bare TiO2 to about 2.05 milliampere per centimeter square for zinc sulfide passivated copper antimony, that is CuSbS2 sensitized TiO2 potanodes. We also carried out this IPC. We also measured the IPC spectra of this photocathode and the photoanode, and we observed there is increased increment in the IPC at about 400 nanometer, less than around 395 nanometers, from about 8% to about 35% after zinc sulfide passivation of this Cu3SbS4 nanocrystals on the NiO photocathode. However, we also observed there is an increment in the visible light absorption after we sensitize this CuSbS3 S4 on the NiO, and the similar observation was found in case of the photoanode as well, that is CuSbS2 sensitized TiO2, which is again passivated by the zinc sulfide. So this visible light, this increment in the absorption in the visible light range, that is about from 450 nanometer to 600 in case of this CuSbS2 sensitized TiO2, and the similar in case of the Cu3SbS2, which is attributed to the visible light absorption capacity or visible light absorption ability of this Cu3SbS4 and the CuSbS2 nanocrystals or the quantum dots. So again, we measured this gas evolution performance, like we carried out the quantitative analysis of this photocathode and photanode separately, and we found out that the photocathode showed the H2 evolution of about 1.52 micromole after reaction or after the test of about 150 minutes for 150 minutes, and about 5.8 micromole in case of the photanode after 150 minutes. Of course, so there is a slight deviation in the stoichiometry of this H2 and O2 because we carried out this measurement in the single electrolyzer. So there is a high probability that this evolved hydrogen and oxygen get recombined again to form the water. So we can of course avoid the recombination of this H2 and O2 by using the two different compartments for the quantitative analysis of this evolved gases from the photanode and photocathode. After we measure this gas evolutions from the photanode and photocathode, we simply overlap the absolute JV curves of this photocathode, that is Cu3SbS4 sensitized the NiO and CuSbS2 sensitized TiO2 photanode, and we found out that a current density intersection of about 0.97 milliampere per centimeter square from the measurement of this individual photocathode and the photoanode that usually illustrate the solar to hydrogen efficiency of about 0.28% for this kind of system. Furthermore, what we did is using this photoanode and photocathode. Of course, until here we measure all these the performances using 3 electrode configuration, where we use the photoanode or the photocathodes, and as a of course these electrodes as a photocathode or a photoanode, platinum as a counter electrode, and the AgCl as a reference electrode. So after that, what we did is we just took this photocathode as a NIO sensitized, Cu3SbS4 sensitized NIO, and the CuSbS2 sensitized TiO2 as a photoanode, and then we just formed the wire link photoelectrolysis cell in a tandem configuration, which was illuminated from the different sides of the photoelectrodes. Initially from the NIO side, and then later on the TiO2 side, and we observed that the illumination from the NIO side, that is from the photocathode side, works better in our case. Of course, that's again because the NIO can be fabricated, can be deposited as a transparent films, whereas TiO2 can't be deposited as a transparent film. Simply, it means the TiO2 is opaque, whereas the NiO2 is slightly transparent, which can allow the light to pass to the photonode, which can again contribute to the improve the photocurrent density. So when we measured the JV current, when the JV curve was measured by eliminating from the photocathode side, the photoelectrolysis cell showed a short circuit current density of about 0.84 milliampere per centimeter square, and the open circuit voltage of about 0.55 volt. So this obtained photocurrent density of 0.84 milliampere per centimeter square, which is near about the same that we achieved by simply overlapping the photocurrent JV curves of this individual photocathode and the photoanode. However, there is a slight decrease in the photocurrent density after fabricating the wire link the photoelectrolysis cell again, which might be due to the leakage in the currents because of the connections of this two wire link electrolysis cell. So after the JV curve measurement, we carried out the stability test measurement, and we found out that the stability was not so promising. Again, which might be due to the corrosion behavior of the sulfide-based compounds, not only limited to this copper antimony sulfide phases, but also the passivation layer that we use, which is the zinc sulfide passivation layer, that is, which is again a sulfide-based compound. So what we believe is that, of course, please note that. So this photocathode as well as the photoanode, they are mostly measured without the addition of the catalyst, which really help to improve the acceleration of this water oxidation as well as the hydrogen evolution reaction. So we haven't studied the effect of the catalyst on the top of this photocathode as well as the photoanode, which is currently undergoing in our laboratory, and hopefully we will achieve the improved solar to hydrogen efficiency for this kind of photoelectrode systems in our case. Again, the stability, not so promising stability, can be again improved by by putting the catalyst on the top of this zinc sulfide passivation layer, or by simply replacing this zinc sulfide passivation layer using the different compounds, such as the phosphide-based compounds or the oxide-based compounds or the hydroxide-based compounds. Again, it highly depends on the band alignment between this Cu3SbS4 and the copper antimony sulfide with this upper layer that we are going to use. Finally, let me conclude today's presentation. So we achieved this efficiency of about 12.07%. Of course, we have recently improved this efficiency to about 12.3%. We haven't reported that work yet, so I did not include that data in today's presentation. So for the CCTSS thin film solar cell can be easily fabricated, could be successfully fabricated using this partial edge substitutions, which is approaching a near to world record efficiency of 12.6%. Note that the achieved 12.6% efficiency is using the highly toxic and flammable hydrogen-based solution approach, where we are using the simply this sputtering-based approach, which can be used for the commercializations. And the second one is a facile and the green deputatic solvent could be used as a solvent for the synthesis of this copper chalcogen and nanocrystal, mainly copper antimony sulfide, and also can be extended to the other family of compounds. We are trying to make this copper tin sulfide or the copper zinc sulfide or copper indium gallium sulfide nanocrystals in our laboratory using the same deputatic solvents, which we will report in near future. So finally, I would like to thank my previous supervisor, Professor Jenu Kim from Chonnam National University, South Korea, my mentors at School of Photovoltaic and Renewable Energy Engineering, Professor Xiaojing Hao, Science Chair Professor Martin Green, and Science Chair Professor Rose Amal, and the Professor Tomu from UNSW. Of course, also, I would like to acknowledge the Australian Research Council for providing me a funding through this Discovery Early Career Researcher Award to establish my own research group here at SPRI UNSW. And also, I would like to thank the European Commission for the Early Career Researcher Award last year. Thank you so much. If you have any questions, I would be happy to answer you those. Thank you.
Thank you very much, Dr. Magesh, for the wonderful presentation. I think there is
some questions
in the chat box.
Yeah, let me find it out.
One question asked by Ruby Thomas. What about the nanocrystal size?
Of course, nanocrystal sizes. Of course, you can. Yeah, nanocrystal sizes. You can tune the sizes either by changing the reaction conditions, like mostly temperature and time, and also by changing the different ligands. In our case, the particle sizes was about 9 nanometer, 9 nanometer, 11 nanometer, and 9, 11, 17, and 20. 9, 11, 25, and 16 nanometer. Of course, again, it depends on the different compounds and their properties. But of course, you can easily tune the nanocrystal sizes by optimizing the different preparative parameters. I hope that's the answer for your questions, because there are a lot of questions. I can't find the questions now. Can you please ask me on the behalf of these participants?
Yeah, one of the participants, Shukdev Pandey, are you there?
Oh yeah, okay, I got that.
Good afternoon, everybody. I had just a very basic question about the first section. Sure. In the initial slides, you showed like the precursor and then the rapid thermal process.
So is this the one? Is it right?
Yeah, this one and maybe the next one, both this and the next one, yes. So here you have these layers of copper, tin and zinc, and then in the rapid thermal process, they transform into this polycrystalline. So like, so the different layers, like they are one over each other. How do they homogeneously mix and form a polycrystalline? Are there like some issues with that, or like it happens like?
Yeah, of course. Yeah. That's a good question, actually. Yeah. So the thing is, like, we deposit this metal precursor using the sputtering method, and then, so of course it's a CZTS here, but actually we are doing the SSC. It's a CZT SSC. What we do is usually, so using this RTA or the RTP, we use the sulfur and the selenium mixed atmosphere to convert this metal precursor into the absorber. Of course, it depends a lot on the annealing temperature and the pressure. So usually this polycrystalline CZTS or the SSC, they form in between the temperature range about 500 to 580. But below that, you may get these secondary phases of the copper antimony sulfide or the zinc sulfide. So the answer to your question is, you need to optimize the temperature, sulfurization or the salination temperature in order to get this copper zinc tin sulfide pure phase.
Right, and like, do the sequencing of the layers also have an effect? Like, if I put tin the first, so like you need to follow a particular sequence of the layering as well.
See the thing, again, see the thing is that sequence matters a lot because during the sulfurization or the salination, the diffusion rate or the diffusion capability of these three elements, copper, zinc, and tin, they are different to each other. So the sequence really matters as well. But again, actually, it doesn't matter on the formation of this phase, but it really matters on the device efficiency.
I see. Interesting.
Yeah.
Okay.
So
okay. I have.
Yeah.
Okay. Thank you for that. I have one or two more questions. Is there time for me to ask?
Sure. Yeah.
Yeah. So, like in the coming slides, there was like this comparative study between samples A, B, C, D. I would like to know what are these samples A, B, C, D? How do they differ? Yeah, this one. Yeah, this one.
Oh, actually, yeah. Okay, I forgot to mention because like
Right.
so this ABCD,
Yeah.
ABCD. So the composition of this A sample, B sample, and C sample, we varied this copper and the Ag contents in these 4 different samples.
Okay.
You may you may refer our recently published papers in the supporting information. You will get this all information.
Sure. Okay.
Or I will just post my email ID here. You can write me anytime you want.
Right, that would be great. So one last question. You studied the effect of Ag. Are there also like like a possibility to study like AU and PT, like being the like used as one of the layers?
Yeah. See. The thing is, again, I don't think so. It's a good idea to use the AU and the platinum because see the our aim is to make these earth abundant compounds, right? And then if you're using this, you got it, right?
Okay, yeah. Thank you so much for answering.
Because there is there is nothing wrong in trying the gold or the platinum. Of course, again, you should understand the which kind of depict they usually they passivate, like gold or the platinum will passivate.
Right.
But again, our aim is to make the earth abundant compound thin film solar cell. So it doesn't make sense to use the gold over the platinum.
Okay. Thank you.
My pleasure. Yeah. Any other question, Dr. Dinesh? I can't find any.
Yes, sir. Only those 2 questions. Participants, if you have any questions, please click the raise hand option. That we will allow you to interact with the speaker.
I hope I have finished in time to answer the questions.
Yes,
right?
That's absolutely right. You have finished the time. One of my questions regarding this kind of chalcogenides, what about that coefficients that is charge coefficient that will transfer the electron current, that everything?
Charge coefficient. I didn't get it. What do you mean exactly? You mean the charge transport mechanism?
Charge transfer properties for this mechanism regarding when we incorporate like any plasmonic material like Ag, like that, or if we incorporate any transition metals like nickel, copper, iron, zinc, that kind of material. What about that charge transport efficiencies?
I don't know exactly the answer for your question because like I never work with the transition metals alloying into these compounds. But with my experience, I would suggest you that's not a good idea to incorporate these transition metals. So because the reason is probably our intention is to passivate the deep level defects in these compounds. And what we found out that the alloying or substituting these transition metals probably will not lead to passivation of these defect densities or the defects in the CZT SSE. So of course, I'm not so expert in this one. So I don't know exact answer, but you may find out somewhere in the literature. But my personal opinion is it's not a good idea to, to consider the transition metals for CZT SSE.
And another one, sir, what about these chalcogenide materials applicable for counter electrode in perovskite solar cell applications?
I don't know. I don't know exactly, but of course, like we are mainly trying to work on the light absorbing compounds. We haven't studied the application of these copper chalcogenides as a counter electrodes, but I have seen few papers. They work well, but again, the problem, as I said in my last few slides, these chalcogenide compounds, because they contain usually the sulfur and the selenium, right? And the counter electrode, so this dye-sensitized or the perovskite, not sure about the perovskite because I think these are the solid state, but when you say as a counter electrode, in case of the dye-sensitized, the stability of this CZT SAC is not so good in the aqueous electrolytes. So that can be another question. And in case of the perovskite, I'm not sure it's a good idea to use the CZT SAC as a counter electrode in the perovskite, because you can find a lot more different counter electrodes for the perovskite, which are really efficient compared to this CZTS or SSC compounds or the other copper chalcogenic compounds. I think this copper chalcogenic compounds, such as this CZT-SSC or the CHS or the copper antimony sulfide, they are mainly light absorbing compounds, and they have this high absorption coefficient. So rather, I would consider utilizing these compounds in the light absorption applications, such as solar cell or the solar PLs, rather than utilizing these compounds as a counter electrodes. Okay, that's just my personal opinion.
Thank you, sir. Thank you, Dr. Magesh. And participants, if
My
you
pleasure.
have any questions or else if you want to interact with the speaker, please click the raise hand option. That will allow you to interact with the speaker. Okay, Dr. Magesh, there is no questions in the chat box. On behalf of the organizing committee of this eSTEM21 and our management, Chetna College of Engineering and Technology, faculty members, principal, administrative officer, we very thank you for your time and your presentation, excellent presentation on this topic. Thank you so much, Dr. Magesh.
Yeah, thank you, Dr. Dinesh. Actually, it was a good experience for me to attend and give my presentation in this work in this international conference. I'm pretty sure I know a lot of presenters in this e-conference. I know many of them, Professor Aidil and few of them. I know them personally, so it's a really a good speaker line for this conference. Thanks for the invitation, and I will be in touch with you. Thank you.
Yeah, sure. Thank you, Professor Magesh.
Yeah, have a good time. Bye-bye. Yeah.
And yeah, thank you so much. And your information for the participants. So the next session will begin at 1:30 p.m. Dr. Monica Lira from the nanostructural materials for photovoltaic energy from ICN to Spain will be delivering the talk. Please try to join the link around 1:15 p.m. Also, there will be the same meeting will be telecasted live in our college website YouTube page. You are requested to fill the feedback for the first session and this session, second session too. The link were posted in the chat box. Kindly find them and fill them. That will be improve us to conduct upcoming workshops, webinars will be much more effective. Thank you for your time. I request you kindly fill the feedback form, and after that you can leave the meeting. Thank you so much. Thank you so much, participants.